Everything we know, every planet, star, and galaxy, came from a single moment, the Big Bang. In an instant, the universe was born from nothing, expanding into the vast cosmos we live in today. But how does something emerge from nothing? What triggered this event? And if there was truly nothing before the Big Bang, what does that even mean? Was there an empty void waiting for the universe to appear? Or was nothing a state so bizarre that our understanding of physics simply can't explain it? Some theories suggest that the Big Bang wasn't the beginning at all, that something existed before it. From quantum fluctuations and extra dimensions to bubbling multiverses and bouncing universes, let's explore ideas about what may have sparked everything into existence. Charting the pre-Big Bang landscape, early conditions and possibilities. The idea of the Big Bang as the absolute beginning of the universe has long been a dominant concept in cosmology. However, modern physics has opened the door to the notion of a pre-Big Bang landscape. Some theories suggest that the universe may have had a past, governed by conditions that were vastly different from anything we can observe today. Exploring this landscape is difficult because there is no direct evidence from before the Big Bang. However, theoretical models allow us to map out possible scenarios and glimpse what the cosmos might have been like before it exploded into existence. It is possible that the universe existed in a timeless quantum state before the Big Bang. Instead of a hot, dense singularity, the early universe could have been a quantum fluctuation in a vast, pre-existing energy field. This idea is supported by the principles of quantum mechanics, which suggest that even what seems like nothing is never truly empty. If a quantum fluctuation reached a certain threshold, it could have triggered the birth of the universe, causing space and time to emerge from this pre-existing quantum landscape. Another theory suggests that the universe did not have a definite beginning, but instead has gone through endless cycles of expansion and contraction. This cyclic universe model proposes that the Big Bang was not a unique event but just one phase in an infinite cosmic cycle. In this view, the universe expands, cools, and then eventually contracts back into a dense state, which leads to another Big Bang-like event. Some versions of this idea propose that each cycle is slightly different, with physical laws and structures changing in each new era. This could mean that the fundamental constants of nature, things like the strength of gravity or the charge of the electron, may have evolved over time. If true, the universe we observe today may just be one version of many, shaped by conditions in the previous cycle. Perhaps the universe is part of a much larger, higher dimensional structure, as explained by string theory. In this model, what we perceive as the Big Bang may have been the result of a collision between higher dimensional branes, vast membrane-like objects that exist in extra dimensions beyond our familiar three of space and one of time. These brane collisions could create new universes, each with its own unique properties. If this is the case, then our universe is just one bubble in a much larger cosmic landscape, and the Big Bang was simply a localized event within a much grander structure. According to the theory of cosmic inflation, a fraction of a second after the Big Bang, the universe underwent a brief but extremely rapid expansion, growing exponentially before settling into a slower rate of expansion. However, some versions of inflationary theory suggest that inflation itself may have existed before the Big Bang, in a timeless state, with random quantum fluctuations determining when and where new universes formed. If true, this would mean that the Big Bang was not a singular event, but one of many, with different regions of the cosmos continuing to inflate and give rise to new universes. Some take this idea even further and suggest that our universe is part of a vast multiverse, a collection of many different universes, each with its own properties. In this scenario, the conditions before the Big Bang could have included countless other universes, each forming and evolving according to its own set of physical laws. Some of these universes may have collapsed, while others continued expanding indefinitely. If this idea is correct, then what we think of as the beginning of everything may actually be just one part of an unimaginably large and complex cosmic structure. Some particularly speculative ideas even suggest that before the Big Bang, there was no space, no time, and no matter, only pure information, or a yet unknown fundamental structure from which everything emerged. In this view, the universe as we see it could be a manifestation of deeper, more abstract rules that govern reality. If this is the case, understanding what came before the Big Bang may require a completely new way of thinking about existence itself. The quantum vacuum, unveiling the subtle structure of nothing. Of all the ideas that shape our understanding of the universe, few are as counterintuitive as the nature of empty space. Throughout history, a vacuum was thought to be a true void, an absence of matter, energy, and structure. The ancient Greeks debated whether a vacuum could even exist, while early scientists envisioned it as a perfect nothingness, a backdrop against which physical objects moved. Even into the 19th and early 20th centuries, the vacuum of space was thought to be an empty expanse, a silent and motionless void where nothing could happen. But as science progressed, this perception changed. The emergence of quantum physics in the 20th century revealed a profound truth. What we call empty space is not empty at all. Instead, it is a restless, ever-changing landscape filled with invisible energy and fluctuations that constantly ripple through reality. Even in the absence of matter, even in the coldest and most isolated corners of the cosmos, space itself is alive with activity. What we once thought was nothing is in fact a hidden structure of something. At the core of this revelation is the concept of quantum fluctuations. Unlike the classical understanding of physics, which suggests that a vacuum is completely still and devoid of energy, quantum mechanics describes a world where uncertainty reigns at the smallest scales. The famous Heisenberg uncertainty principle states that it is impossible to precisely determine both the energy and time characteristics of a system simultaneously. This means that energy can never be exactly zero. Instead, space is filled with unpredictable fluctuations, brief bursts of energy appearing and disappearing in an instant, even when no particles seem to be present. These fluctuations give rise to something extraordinary: virtual particles. These are not like the atoms or subatomic particles that make up the matter we see around us. Instead, virtual particles exist only for the tiniest fractions of a second before vanishing back into the quantum vacuum. They never stay long enough to be directly observed, but their presence is undeniable. In fact, their effects can be measured in ways that provide compelling evidence for their existence. One of the most striking demonstrations of this hidden energy is the Casimir effect, an experiment named after Dutch physicist Hendrik Casimir. In this experiment, two uncharged metal plates are placed extremely close together in a vacuum. Classical physics would predict that without any external forces acting on them, the plates should remain stationary. However, something unexpected happens. They are pushed toward each other by an invisible force. This occurs because the energy fluctuations between the plates are different from those in the surrounding vacuum. The result is a measurable force that seems to come from nowhere, yet it is a direct consequence of the quantum vacuum's ever-present fluctuations. Another remarkable consequence of the quantum vacuum is a phenomenon called vacuum polarization. Even in a vacuum, virtual particles constantly emerge and disappear, affecting the behavior of real particles. For instance, when an electron moves through space, it does not travel alone. Instead, it is surrounded by a swarm of virtual particles that influence its charge and mass. These effects have been observed in high-energy physics experiments, providing further evidence that the vacuum is not an empty void, but an active and dynamic environment. Some scientists believe that the vacuum itself could hold the key to one of the greatest mysteries in modern physics: dark energy. Observations of distant galaxies have shown that the universe is expanding at an accelerating rate, a phenomenon that defies traditional gravitational models. One possible explanation is that the vacuum is filled with energy, exerting a repulsive force that drives cosmic expansion. This so-called vacuum energy, also known as the cosmological constant, could be the hidden force shaping the fate of the universe. Yet, despite its profound influence, the quantum vacuum remains one of the least understood aspects of physics. The amount of energy predicted by quantum mechanics is vastly larger than what is observed in astrophysical measurements. This discrepancy, sometimes referred to as the vacuum catastrophe, is one of the biggest unsolved problems in modern science. If the vacuum is teeming with energy, why doesn't it have a stronger effect on the cosmos? And if it does, what is keeping it in balance? The more we study the quantum vacuum, the more it challenges our assumptions about the universe. What was once thought to be an empty void turns out to be a rich and complex structure, a sea of ever-present energy shaping the fabric of existence. Zero-point energy and spontaneous symmetry, breaking in the void. Even in the coldest and most isolated parts of the universe, where there seems to be nothing at all, space is never truly empty. It is filled with an invisible form of energy known as zero-point energy. This energy is the lowest possible state of a quantum system, but even at this minimum level, fluctuations never stop. One of the most intriguing ideas related to zero-point energy is its connection to spontaneous symmetry breaking. In physics, symmetry describes the idea that certain properties of a system remain unchanged under different conditions. But sometimes, a system can shift unexpectedly, breaking this symmetry and leading to dramatic changes. This kind of shift can happen when tiny fluctuations, like those caused by zero-point energy, push a system past a critical point. A simple way to think about symmetry breaking is to imagine a perfectly balanced ball sitting on top of a hill. In theory, the ball should stay there forever, as the hill is symmetrical in every direction. But in reality, even the slightest disturbance, like a breath of wind or a tiny vibration, can push the ball to one side, causing it to roll down. The symmetry is broken, and a new state is created. In the universe, similar processes can happen at an unimaginably large scale, triggered by energy fluctuations in the vacuum. This idea plays a major role in how scientists believe the early universe evolved. Right after the Big Bang, the universe was in a hot, highly energetic state, filled with quantum fluctuations. As it expanded and cooled, these fluctuations influenced the way fundamental forces and particles took shape. In the early moments, all the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified as a single force. But as the universe cooled, spontaneous symmetry breaking caused these forces to separate, forming the distinct interactions that govern the universe today. One of the most famous examples of this kind of symmetry breaking is the Higgs mechanism, which explains how particles gain mass. In the early universe, all particles may have been massless, but as space cooled, the Higgs field, a quantum field spread throughout space, underwent spontaneous symmetry breaking. This led to the creation of the Higgs boson, a particle that interacts with other particles and gives them mass. Without this process, atoms and galaxies would never have formed, and the universe as we know it would not exist. During inflation, the universe expanded at an incredible speed, far faster than it does today. Some theories suggest that a shift in the quantum vacuum triggered this expansion, causing space to stretch rapidly. If this is true, then zero-point energy and vacuum fluctuations may have shaped the largest structures in the cosmos, setting the stage for everything that followed. The nature of zero-point energy is still not fully understood, and the connection between vacuum fluctuations and cosmic events is an area of ongoing research. If the vacuum is not just a passive background but an active player in the structure of the universe, it could hold answers to some of the biggest mysteries in science, such as the Big Bang itself. From uncertainty to existence, the emergence of spacetime. In classical physics, space is often thought of as an empty stage, a backdrop against which the universe unfolds. Time, in turn, is seen as a steady, unchanging progression from past to future. But quantum mechanics suggests that, at the smallest scales, space and time may not be fundamental at all. Instead, they could be the product of more basic quantum interactions, arising from an underlying sea of randomness. One idea is that spacetime itself may emerge from quantum entanglement. Entanglement is one of the most mysterious properties of quantum mechanics. When two particles become entangled, they remain linked no matter how far apart they are. A change to one particle instantly affects the other, even if they are separated by vast distances. This phenomenon has been demonstrated in experiments and is now considered a well-established feature of the quantum world. Some physicists believe that if enough quantum systems become entangled, they can generate the very structure of space. In this view, space is not a passive emptiness, but rather a vast web of entangled particles. The fabric of the universe may be nothing more than a complex network of these quantum connections. At large scales, this network behaves like the continuous spacetime we experience, but at the smallest scales, space could be fragmented, woven from countless tiny links between quantum states. If true, this means that space is not something that simply exists on its own. It is a byproduct of deeper quantum interactions. Beyond entanglement, another approach suggests that space and time may emerge from something even more fundamental, quantum uncertainty itself. At the smallest possible scales, quantum mechanics tells us that nothing is ever truly at rest. Energy and particles constantly fluctuate in and out of existence, appearing and disappearing in ways that defy classical logic. If space and time were not fixed structures, but instead emerged from this fluctuating background, then in the earliest moments of the universe, they might not have existed at all. The idea of a pre-space, or a state before space and time had formed, is difficult to imagine. In this picture, there was no defined distance between points, no clear direction, no past or future. Instead, there was a chaotic, ever-changing state where quantum laws operated without the familiar constraints of spacetime. It was from this uncertainty, some theories suggest, that spacetime itself took shape. Just as ice forms from liquid water when temperatures drop, the structured universe we see today may have crystallized out of this formless quantum haze. Some theoretical models propose that space is made of tiny, indivisible units, almost like the pixels on a digital screen. In classical physics, space is thought to be infinitely divisible. No matter how small a region is, it can always be divided further. But if space is made up of discrete building blocks, then beyond a certain limit, it may no longer make sense to talk about distances at all. This idea is central to loop quantum gravity, a theory that suggests space is composed of tiny loops that interconnect to form the fabric of the universe. These loops are so small that they are far beyond anything we could ever observe directly, but their existence could help explain why space behaves the way it does. Time, too, may be something that emerges rather than something fundamental. In our everyday experience, time moves forward in a smooth, unchanging flow. But in quantum mechanics, time is not always so straightforward. At very small scales, the distinction between past, present, and future becomes blurred. Some quantum systems do not have a clear order of events. Their states evolve in a way that does not follow the familiar forward-moving clock. Some researchers believe that time is closely linked to entropy, the measure of disorder in a system. The universe always moves from lower entropy or more order to higher entropy or more disorder. This increase in entropy gives rise to the arrow of time, the direction in which time seems to flow. But in the early universe, when everything was in a highly ordered state, time may not have behaved in the way we are used to. Instead of progressing smoothly forward, it may have been more like a fluctuating, uncertain property, only stabilizing as the universe expanded. In classical physics, a black hole is a region of space where gravity is so strong that nothing, not even light, can escape. But if space itself is built from quantum connections, then the nature of black holes may be very different from what we expect. Perhaps the interior of a black hole is not an empty void, but a tangled network of entangled quantum states, possibly even linked to other regions of the universe. If there was a time before space and time as we know them existed, then the Big Bang may not have been a sudden explosion from a single point. Instead, it could have been a gradual unfolding of structure from a pre-existing quantum state. Some theories, such as the holographic principle, suggest that the universe itself might be a projection from a deeper, more fundamental layer of reality, one where space and time are not primary concepts, but byproducts of something even more abstract. Physicists continue to explore these questions, searching for evidence that could confirm or challenge these theories. Some experiments, such as those studying gravitational waves or high-energy particle collisions, may provide hints about whether spacetime is truly fundamental or just one layer of a deeper reality. Bridging the divide, merging quantum mechanics with general relativity. Physicists have spent more than a century trying to understand the two most powerful theories in modern science, quantum mechanics and general relativity. Each describes the universe with extraordinary precision, but they apply to very different realms. Quantum mechanics governs the world of the very small, where particles can exist in multiple places at once and change their states unpredictably. General relativity, on the other hand, explains how gravity shapes the universe at large scales, from planets to galaxies, to the vast structure of the cosmos itself. Both theories have been tested and confirmed by countless experiments, yet they seem to be fundamentally incompatible with each other. In general relativity, space and time form a smooth, continuous fabric that can be stretched and curved by massive objects. This curvature is what we experience as gravity. The presence of a star, planet, or black hole bends the space around it, affecting the motion of other objects nearby. This idea has been confirmed through observations such as the bending of starlight around the Sun and the precise measurements of gravitational waves. Quantum mechanics, meanwhile, suggests space and time are not smooth at all. Instead, at the smallest possible scales, space itself may be made up of fluctuating quantum energy, where uncertainty and randomness dominate. At this level, particles do not follow clear paths but exist in a haze of probabilities, interacting in ways that seem to break the normal flow of cause and effect. The trouble begins when physicists try to apply quantum mechanics to gravity. When they attempt to describe gravity using the same mathematical framework as other forces, like electromagnetism or the nuclear forces, the equations stop making sense. The calculations produce infinities, results that have no physical meaning, suggesting that something fundamental is missing from our understanding. General relativity and quantum mechanics work perfectly well in their own domains, but when they meet, such as in the intense gravity of a black hole or the extreme conditions of the early universe, their rules seem to clash. One of the biggest challenges comes from what happens at incredibly small scales. If space is truly made of discrete building blocks at the smallest scales, then general relativity, which relies on space being smooth, cannot describe reality at those levels. This fundamental contradiction has led physicists to search for a theory that can unite these two worlds. One possible solution is string theory. Unlike traditional physics, which treats particles as single points, string theory proposes that all particles are actually tiny vibrating strings. These strings can oscillate in different ways, with each type of vibration corresponding to a different particle. The theory suggests that gravity is simply one of these vibrations, just like the particles of light or matter. If true, this would mean that quantum mechanics and gravity are not separate forces, but different aspects of the same fundamental structure. String theory also introduces extra dimensions of space. These extra dimensions could be curled up so small that they are invisible to us, yet they could provide a way to merge quantum mechanics with general relativity. However, string theory is highly complex and has yet to be confirmed by experiments. So far, no direct evidence of extra dimensions or vibrating strings has been found, leaving physicists searching for other possible explanations. While promising, loop quantum gravity also lacks direct experimental evidence, and much work remains to be done to determine whether it is a valid description of nature. Some researchers believe that the key to solving this problem lies in studying black holes. According to general relativity, the core of a black hole, known as the singularity, is an infinitely small point. But in quantum mechanics, infinities are a sign that something is missing from the theory. If space and time truly break down at a black hole center, then quantum mechanics should play a role in describing what happens there. Understanding black holes at the quantum level could provide clues about how to merge gravity with the laws of the very small. In the 1970s, physicist Stephen Hawking showed that black holes are not completely black. They slowly emit radiation due to quantum effects near their event horizons. This radiation, known as Hawking radiation, suggests that black holes could eventually evaporate over time. But if a black hole disappears, what happens to the information about everything that fell into it? Quantum mechanics says that information cannot be destroyed, yet general relativity seems to suggest otherwise. This paradox, known as the black hole information problem, has led to intense debate and could be a crucial piece in bridging the gap between quantum mechanics and gravity. Some scientists have proposed that black holes might act like holograms, where all the information about what falls inside is stored on the surface, much like a 3D object being represented on a 2D screen. The universe itself might work in a similar way. If true, this could offer a way to connect quantum mechanics and gravity, showing that spacetime itself emerges from deeper quantum principles. Another possible clue comes from the study of gravitational waves, ripples in spacetime created by massive objects like merging black holes. Since their first detection in 2015, gravitational waves have provided new ways to test general relativity under extreme conditions. Some researchers hope that by studying them more closely, we might find subtle quantum effects that could hint at a deeper connection between gravity and quantum mechanics. The Hartle-Hawking no-boundary proposal, a universe without a beginning. The idea that the universe had a definite beginning is one of the most deeply ingrained concepts in modern cosmology. The standard Big Bang model suggests that everything emerged from an extremely hot and dense state around 13.8 billion years ago. But this description runs into problems when pushed to its limits, suggesting that our understanding of the beginning of time is incomplete. An alternative to this classical view is the Hartle-Hawking no-boundary proposal. This theory, proposed by physicists James Hartle and Stephen Hawking in the early 1980s, offers a different perspective on the origin of the universe. Instead of assuming that time had a distinct beginning, the no-boundary proposal suggests that time and space smoothly transition into one another in the early universe, eliminating the need for a singular starting point. In this view, the universe has no sharp beginning, but rather a smooth, finite history that does not require an external cause or a moment of creation. The no-boundary proposal suggests that, at extremely small scales, time might behave more like space. This means that as we go further and further back in cosmic history, time does not simply reach a hard stop at a singularity. Instead, it transforms smoothly into a spatial dimension. In this view, asking what happened before the Big Bang is meaningless because there was no before in the conventional sense. Time, as we experience it, simply emerges from this earlier, more fluid state of reality. A helpful analogy is the North Pole. If you walk north on Earth, you eventually reach the North Pole, but there is no meaningful concept of going further north beyond that point. North simply ceases to exist. Similarly, in the Hartle-Hawking model, the past does not extend infinitely backward in time. Instead, time gradually emerges from a state where it behaved like space. The universe, according to this theory, did not have a singular beginning, but instead existed in a rounded finite state that smoothly transitioned into the expanding universe we see today. If the universe did not begin in a singularity, it means that space-time could have always existed in some form without a distinct point of origin. It also removes the need to explain what caused the Big Bang because, in this model, the universe's existence is self-contained. There is no initial moment that needs an external cause. Quantum mechanics and general relativity together provide a natural way for the universe to exist without requiring a first cause. This is a radical departure from traditional cosmological models, which assume that time has a definite starting point. The no-boundary proposal suggests that the universe could be eternal in a sense, though not in the way classical physics might define eternity. Mathematically, the Hartle-Hawking proposal relies on a concept called imaginary time. This idea, drawn from quantum mechanics, suggests that time can be treated as a complex number rather than a simple linear sequence. In normal circumstances, time follows a real number path. Seconds tick forward one after another. But in extreme conditions, like those found in the early universe, time could have taken on an imaginary component, blending with space rather than existing as a separate dimension. This allows for a smooth, finite geometry for the universe without a singular starting point. While this idea is elegant in theory, it raises several questions. If time emerged from a more spatial-like state, how did it transition into the familiar flowing time we experience today? What determined the structure of this early quantum state? And does this model accurately describe what happened, or is it just a mathematical convenience? Observational evidence is difficult to gather, but some clues might come from the cosmic microwave background, or CMB, the faint glow left over from the early universe. This radiation carries information about the conditions of the universe in its infancy, and scientists are searching for signatures that could hint at whether time behaved differently at those scales. Small variations in the CMB could provide insights into whether space and time followed a no-boundary model, or if another explanation is needed. Deeper studies of these ancient signals could one day confirm or rule out the Hartle-Hawking proposal. If this proposal is correct, then the early universe did not emerge from a singularity, but rather from a smooth quantum state that transitioned into the expanding cosmos we observe today. This would mean that the laws of physics were always in place, and that the universe is ultimately a product of these laws, rather than an event that required an external trigger. While this does not answer all questions about existence, it provides a new way of thinking about the origins of the universe, one that does not rely on traditional notions of time and causality. In practical terms, this means that our current understanding of physics may need to be revised. The true nature of reality may be governed by deeper principles of quantum mechanics that have yet to be fully understood. Some researchers believe that a complete theory of quantum gravity could provide further insights into this process. This shift in perspective also has philosophical implications. If the universe has no clear beginning, then questions about what happened before the Big Bang become meaningless. Instead, we must ask different questions. How did space-time emerge from a quantum state? What underlying principles determine the structure of reality? And if the universe does not require a beginning, does it also not require an end? Eternal inflation. Infinite bubbles in a boundless multiverse. Unlike the standard Big Bang theory, which describes a single event that set everything into motion, eternal inflation proposes that the rapid expansion of space never truly ended. Instead, different regions of the cosmos experience this inflation at different times, creating countless bubble-like universes, each with its own unique properties. This means that our universe, vast as it may seem, could be just one of many in an endless multiverse. Each of these bubble universes could have different physical laws and fundamental constants. Some might have different strengths of gravity, different numbers of spatial dimensions, or even different types of particles and forces. Some universes might be completely hostile to life, while others might have conditions even more favorable than our own. The physics that we take for granted, things like the charge of an electron or the speed of light, may be just specific to our bubble, with entirely different rules applying elsewhere. One of the most fascinating implications of eternal inflation is that it naturally leads to a multiverse. If inflation is an ongoing process that never stops completely, then it produces an infinite number of universes over time. Each bubble universe forms when inflation slows down in a particular region. But inflation itself continues in the vast space beyond. This means that while our universe seems to have a well-defined beginning, it is actually part of a much larger, dynamic system where new universes are constantly being created. If infinite bubble universes exist, then every possible outcome might happen somewhere in the multiverse. There could be other versions of our universe where history unfolded differently, with alternate versions of stars, galaxies, and even civilizations. In some bubbles, physics might be so different that complex structures like atoms could never form. In others, the conditions could be nearly identical to our own, leading to universes that are eerily similar to ours. Some researchers believe that evidence for eternal inflation could be hidden in the CMB. If our bubble universe once interacted with another bubble in the past, it might have left detectable imprints in this ancient radiation. Scientists are looking for subtle patterns that could hint at collisions between universes, but so far, no clear evidence has been found. If the multiverse is truly infinite, then the concept of probability becomes difficult to define. In an infinite system, anything that can happen will happen an infinite number of times. This makes it hard to determine why our universe has the properties it does and why we observe the laws of physics that we do. Some physicists propose that the conditions in our universe might simply be a result of selection. Only universes with the right conditions for observers like us will have anyone in them to ask these questions. False vacuums, metastable states, and the spark of expansion. The vacuum of space as we experience it might not be in its most stable state. Instead, it could be a metastable state, one that appears stable over vast periods of time, but is actually at risk of transitioning to a more stable state. In physics, a vacuum is often thought of as the lowest possible energy state. However, in some theories, what we consider a vacuum might actually be a false vacuum. This means that it is not the true lowest energy state, but a local minimum, like a ball resting in a shallow dip on a landscape of hills and valleys. The ball seems stable in the dip, but if given enough energy, it could roll down into a deeper valley, reaching a more stable state. This shift from a false vacuum to a true vacuum could have enormous consequences for the universe. In the early universe, if space was in a false vacuum state, it would have been filled with energy that was temporarily trapped. This excess energy would have fueled a rapid expansion, stretching space at an exponential rate. This is one way to explain cosmic inflation. The transition from a false vacuum to a true vacuum can happen through a process called quantum tunneling. This means that even if the false vacuum seems stable, random quantum effects could cause a tiny region to tunnel into the true vacuum state. When this happens, a bubble of true vacuum forms and begins to expand at incredible speeds. If this happened in the early universe, it would have caused inflation to stop in that region while still continuing elsewhere, creating pockets of space that became distinct bubble universes. If our universe is still in a false vacuum state today, it means that a vacuum transition could theoretically occur at any time. If a true vacuum bubble formed somewhere in space, it would expand at nearly the speed of light, converting everything in its path to a new state of existence. The laws of physics could change inside this bubble, with different forces, particles, and fundamental constants. However, given the immense timescales involved, this possibility is more of a theoretical curiosity than an immediate threat. One of the challenges of studying false vacuums is that we have no way to directly observe whether our vacuum is truly stable or not. However, particle physics experiments, such as those conducted at the Large Hadron Collider, or LHC, provide some hints. The properties of the Higgs boson, for example, suggest that our universe might be in a metastable vacuum, rather than an absolutely stable one. This means that in the far future, a vacuum decay event could theoretically occur. If the universe emerged from a false vacuum state, then the very nature of space and time is deeply connected to energy fluctuations at the smallest scales. The way the universe expands, the way forces interact, and even the existence of matter itself could all be linked to vacuum stability. If our vacuum is false, then the universe as we know it is only a temporary arrangement, and a more stable state could eventually take over. If this is the case, then the universe might not end through heat death or a big crunch, but instead through a sudden transformation into an entirely different state of reality, one where the rules of physics might be completely rewritten. The ekpyrotic scenario, brain collisions, and cosmic rebirth. In the search for the origins of our universe, an alternative to the traditional Big Bang model emerges from the field of string theory. This is the ekpyrotic scenario, a theory that proposes our universe was born not from a singular explosion, but from a collision between vast, higher dimensional structures known as brains. Unlike the standard picture of cosmic inflation, which describes space expanding rapidly from a hot and dense state, the ekpyrotic model suggests that everything we see today came into existence when two enormous brains, floating in a higher dimensional space, smashed together. In this framework, our universe is not alone. Instead, it exists as a three-dimensional brain embedded within a larger, multi-dimensional space called the bulk. Other brains may exist in parallel, separated from us by an extra spatial dimension we cannot directly perceive. While these brains may be invisible to us, their presence could be responsible for the entire history of our cosmos. The ekpyrotic model suggests that before our universe took shape, these parallel brains drifted through the bulk, each existing independently. Over vast stretches of time, small forces nudged them closer until, eventually, they collided. This moment of impact released an enormous amount of energy, flooding the newly formed universe with radiation and matter. The process was not an explosion in the conventional sense, but a transformation. One that turned the collision into a new reality, where energy condensed into particles and space itself began expanding. In inflationary theory, the smoothness of the universe arises because of a brief but intense expansion that stretched out any irregularities. In the ekpyrotic model, this uniformity is established before the brains collide. As the brains approach each other, small differences in their structure smooth out, leading to a universe that already has a balanced distribution of energy before the collision even happens. This means that, rather than needing an ultra-rapid phase of inflation to explain the cosmos, the universe naturally emerges in an organized state. In traditional Big Bang cosmology, the question of what happened before the Big Bang is difficult to answer because time and space are thought to emerge from the singularity itself. In contrast, the ekpyrotic model suggests that time existed before the collision. The brains had a history before they met, implying that the cosmos may go through endless cycles of destruction and rebirth. According to some extensions of the model, the universe does not just emerge from a single brain collision, but undergoes repeated cycles of expansion and contraction. After a long period of growth, the universe slowly collapses, drawing the brains together again. When they collide, a new universe is born, and the process begins anew. If this is the case, then the cosmos has no true beginning or end, only an eternal pattern of renewal. While inflationary models have been successful in predicting features of the CMB, the ekpyrotic scenario makes slightly different predictions. Scientists have proposed searching for specific patterns that might provide evidence of a brain collision rather than inflation-driven expansion. Although no definitive proof has yet been found, researchers continue to explore whether signatures of the ekpyrotic model might be hiding in the data. If our cosmos is just one brain among many, then it is possible that other universes exist on separate brains, forever hidden from our view. Another open question is how exactly the brain collision translates into the physical laws we observe today. If the energy released during the impact gave rise to matter and radiation, why do the fundamental forces behave the way they do? Some researchers speculate that the structure of the brains themselves determines the nature of physics in the resulting universe. This means that slight variations in how the brains collide could lead to universes with vastly different properties. Hidden dimensions, the role of extra dimensions in cosmic origins. The universe we see is defined by 3 spatial dimensions, along with the passage of time. This 4-dimensional framework forms the foundation of our everyday reality. Yet, some of the most advanced theories in physics suggest that these dimensions are not the full extent of existence. Hidden beyond our perception, extra dimensions may exist, shaping the universe in ways that we cannot directly observe. These unseen dimensions could have played a fundamental role in the birth of the cosmos. In string theory, the properties of strings, such as their mass and charge, depend on the way they vibrate. However, for these vibrations to behave in a way that matches the physical laws we observe, string theory requires additional dimensions beyond the familiar 3. In most versions of string theory, the universe is thought to have at least 10 dimensions, 9 of space and 1 of time. Since we do not perceive these extra spatial dimensions, physicists propose that they are compactified, meaning they are curled up so tightly that they remain hidden from our direct experience. These curled-up dimensions could be smaller than subatomic particles, woven into the very fabric of spacetime. Despite their invisibility, they may influence everything from the behavior of fundamental forces to the very formation of the universe. If extra dimensions exist, then what we perceive as a 3-dimensional universe could actually be a lower dimensional surface embedded within a higher dimensional space. This idea is central to brain-world cosmology. If this is the case, then the early universe may have been influenced by forces acting in these extra dimensions. The presence of extra dimensions also affects the way gravity behaves. In our everyday experience, gravity follows an inverse square law. Its strength diminishes with distance. However, in a universe with additional dimensions, gravity might behave differently at very small scales. Some theories suggest that gravity is actually much stronger than it appears, but is leaking into extra dimensions, making it seem weak in our 3-dimensional world. This could explain why gravity is so much weaker than the other fundamental forces, such as electromagnetism. If extra dimensions exist, they might allow for the creation of exotic particles or even microscopic black holes, offering experimental evidence of a reality beyond our 3-dimensional space. Some physicists speculate that certain forms of dark matter, the invisible substance that makes up much of the universe's mass, might actually be particles confined to another brane, affecting our universe only through gravity. String theory. Perspectives, vibrations, and the fabric of pre-cosmic reality. In traditional physics, particles such as electrons, quarks, and photons are treated as individual points with no internal structure. This description has worked well for much of modern science, but it leads to deep inconsistencies when trying to combine the laws of quantum mechanics with the force of gravity. String theory offers a different perspective. The interactions between strings allow for a unification of forces, suggesting that gravity, electromagnetism, and nuclear forces are all different manifestations of the same underlying structure. Just as different musical notes come from different vibrations of a guitar string, the properties of subatomic particles arise from the way fundamental strings vibrate. The frequency of vibration determines whether a string behaves like an electron, a photon, or even a graviton, the hypothetical particle that carries the force of gravity. In this way, string theory provides a new way to understand the diversity of particles and forces that shape the cosmos. Because these strings are so small, many times smaller than a proton, directly observing them is impossible with current technology. However, their effects may still be seen in the large-scale structure of the universe. The patterns of the CMB, the way gravity behaves at extreme scales, or even the presence of unknown particles at high-energy colliders, could all provide indirect evidence for the existence of fundamental strings. Instead of assuming spacetime as a fixed stage where particles move, string theory envisions spacetime as a dynamic fabric woven by the relationships between strings. This could help explain some of the greatest mysteries in cosmology, such as what happened before the Big Bang, and whether spacetime itself can emerge from a more basic structure. A key feature of string theory is its reliance on extra dimensions. The shape and size of these hidden dimensions determine how strings vibrate, influencing the very nature of reality. The idea that extra dimensions might exist is not entirely new. In the early 20th century, some physicists speculated that gravity could be explained by the existence of an unseen dimension. However, it wasn't until string theory that this idea was fully developed. One of the most ambitious goals of string theory is to provide a complete description of the universe, unifying all known forces into a single framework. This would resolve the long-standing conflict between quantum mechanics and general relativity. If string theory is correct, it could offer a way to understand not only how the universe evolved after the Big Bang, but also what conditions existed before it, and whether our universe is just one of many. Loop quantum cosmology, bouncing universes instead of singularities. The foundation of loop quantum cosmology, or LQC, comes from loop quantum gravity, or LQG, a theoretical framework that attempts to unite general relativity with quantum mechanics. In loop quantum gravity, space is made up of tiny, discrete loops. Much like a woven fabric at a microscopic level, these loops, although incredibly small, billions of times smaller than the smallest particle, change how gravity behaves at extreme scales. When applied to the early universe, these quantum effects prevent space from collapsing into a singularity, instead creating a repulsive force that triggers expansion. This quantum bounce provides a new way of thinking about cosmic history. Instead of an absolute beginning, LQC suggests that time stretches indefinitely into the past. Before our current expansion phase, there may have been a previous universe that underwent a contraction phase. As it shrank, quantum effects grew stronger, eventually halting the collapse and causing the cosmos to rebound, expanding once more. If this model is correct, our universe is part of an ongoing cycle of contraction and expansion, an endless process of cosmic rebirth. One of the biggest advantages of LQC is that it avoids the mathematical breakdown caused by singularities. In LQC, the bounce replaces the singularity with a smooth, continuous transition from one phase of the universe to the next. This provides a more complete and scientifically satisfying picture of cosmic history. To understand how LQC leads to a bounce, it's important to look at the role of quantum gravity. In classical general relativity, gravity is always attractive, meaning that a contracting universe will inevitably collapse into a singularity. But in LQC, the fabric of space itself has a quantum structure, and this structure modifies gravity at extremely high densities. Instead of continuing to collapse, the universe reaches a minimum size and then rebounds outward. This happens because quantum effects introduce a repulsive force that counteracts gravitational collapse at the smallest scales. Other models, such as the ekpyrotic scenario from string theory, also suggest cycles of cosmic rebirth. However, LQC provides a particularly well-defined mathematical framework grounded in quantum gravity. Unlike many speculative ideas, it is based on detailed equations that can be tested against observations. If future experiments confirm the predictions of LQC, it could have profound implications for our understanding of the universe. Instead of thinking of the universe as having emerged from nothing, we might need to embrace the idea that it has always existed in some form, undergoing endless cycles of contraction and expansion. One of the challenges in verifying LQC is that the physics of the early universe is incredibly difficult to probe directly. The Planck satellite has provided some of the most precise measurements of the CMB, but even more sensitive experiments will be needed to detect the subtle signatures predicted by LQC. Some scientists have proposed searching for signs of a previous universe in the form of gravitational waves. If a previous universe left behind any lingering effects, they might show up in the structure of these waves. Another avenue of investigation is high-energy physics experiments that simulate the extreme conditions of the early universe. While we cannot recreate the universe's birth in a laboratory, experiments like those at the LHC provide valuable insights into how quantum gravity might behave. If space is truly quantized, it could have implications for black holes, dark matter, and the fundamental forces of nature. Some scientists speculate that the same quantum gravity effects that cause a cosmic bounce might also prevent black holes from collapsing into singularities. Instead of forming an infinitely dense point, matter falling into a black hole might eventually rebound, much like the universe itself does in LQC. This idea is speculative, and LQC is still a developing theory, where many questions remain unanswered. But its ability to resolve the singularity problem and offer testable predictions makes it one of the most exciting alternatives to the traditional Big Bang model. Non-commutative geometry, rethinking the early universe's fabric. In our everyday experience, we can move freely in three directions, and time appears to flow in a consistent manner. This intuitive picture of reality is deeply ingrained in our understanding of the universe. However, when we look deeper, this seemingly natural structure may no longer apply. One of the most intriguing possibilities comes from the concept of non-commutative geometry. At its core, non-commutative geometry suggests that space is structured in a way that certain measurements affect one another, much like how in quantum mechanics, the precise position and momentum of a particle cannot be simultaneously determined with complete accuracy. This means that the geometry of space at the Planck scale, the incredibly tiny scale where quantum gravity effects dominate, could behave in a fundamentally different way than anything we experience in the macroscopic world. This idea stems from the realization that in quantum mechanics, observable quantities do not always behave as simple numbers. Instead, they follow mathematical rules that depend on the order in which they are measured. If space itself follows a similar structure, then the concept of a fixed coordinate system, where every point has a well-defined position, may no longer hold at the smaller scales. One of the most direct consequences of non-commutative geometry is the possibility that space at the quantum level might resemble a fuzzy, probabilistic structure rather than a smooth expanse. This means that locations in space might not be sharply defined, but instead exist in a kind of uncertain, fluctuating state. If this is true, then our conventional understanding of the Big Bang, which assumes a well-defined singular starting point, might be fundamentally flawed. Instead of a universe that began as a sharply defined explosion of space and time, the cosmos might have emerged from a phase where space itself was in a non-classical state, an era where locations and distances could only be described probabilistically. Non-commutative geometry could provide an alternative explanation for what happened before the Big Bang. If space itself was structured differently, it might mean that time, as we understand it, did not exist in the same way. This could explain why singularities appear in classical physics. They are the result of applying normal space-time concepts to a region where those concepts no longer make sense. Instead of a singularity, the early universe might have emerged from an entirely different phase of reality, where space was governed by new quantum rules. Some theories suggest that non-commutative geometry could naturally produce an inflationary phase. Unlike traditional inflation models, where an unknown field drives this expansion, non-commutative effects could lead to similar behavior as a direct consequence of space's fundamental structure. If space itself has a fundamental quantum structure, then the effects of this structure might become more noticeable at cosmological scales. This could mean that the accelerated expansion we observe today is not caused by an unknown energy field, but is instead a manifestation of the deep, hidden properties of space itself. This raises the possibility that non-commutative effects are not just confined to the early universe, but could still be shaping cosmic evolution today. If space is not continuous, then many of our current theories, based on smooth, well-defined coordinates, may need to be reinterpreted. Concepts like distance, motion, and even causality might have to be understood in a new way, where the relationships between points in space are governed by deeper, hidden principles. This could provide insights into why quantum mechanics and general relativity seem so difficult to reconcile. They may be approximations of a deeper, more fundamental framework where space and time emerge as secondary effects. If space is structured in a way that follows quantum rules, then gravity might not need to be treated as a separate force. It could instead be a manifestation of how space interacts with itself at the smallest scales. This would mean that all forces, from electromagnetism to the strong and weak nuclear forces, might be connected through the underlying geometry of space. The next steps in this journey will involve a combination of mathematical breakthroughs, new experimental techniques, and careful analysis of the universe's earliest signals. If the universe was once governed by a different kind of geometry, the evidence may still be waiting for us to find it. The many worlds interpretation, divergent pathways to existence. In the everyday world, choices seem simple. A person might decide between drinking coffee or tea in the morning, and once the choice is made, the other possibility simply ceases to exist. But in the world of quantum mechanics, particles don't have a single defined state until they're measured. Before that, they exist in a state of superposition, meaning they can be in multiple places or conditions at once. The act of measurement is often thought to collapse these possibilities into a single reality. However, one interpretation suggests something far more radical. What if, instead of collapsing, all possible outcomes happen, each within its own separate universe? This is the foundation of the many worlds interpretation, a concept that redefines reality as an endless branching structure of parallel worlds. The many worlds interpretation, or MWI, emerged from quantum physics in the mid-20th century as an alternative to the traditional Copenhagen interpretation, which suggested that quantum possibilities collapse when observed. Physicist Hugh Everett proposed a different view. Rather than collapsing, the universe splits at every quantum event, creating a new reality for each possible outcome. This means that every time a quantum decision is made, whether an atom decays, a photon passes through a slit, or even whether a person decides to turn left or right, new universes form where all possible outcomes play out. Quantum mechanics shows that subatomic particles can exist in multiple states at once, known as a superposition. In laboratory experiments, particles behave as though they are traveling multiple paths simultaneously. The many worlds interpretation takes this observation to its logical conclusion. If quantum mechanics describes reality accurately, then all possibilities must be realized somewhere. Instead of a wave function collapsing into a single state, it continues evolving, with each possible outcome unfolding in a different branch of reality. One of the strangest implications of this idea is that there are countless versions of you. Right now, in another universe, there is a version of you watching this, but sitting in a slightly different position. There is another where you decided to go outside instead. There are universes where you made drastically different life choices, where historical events took different turns, where entire civilizations never existed because a quantum fluctuation nudged reality in another direction. The number of these alternate worlds would be incomprehensibly large, growing exponentially with every passing moment. Many scientists appreciate the many worlds interpretation because it removes the mystery of wave function collapse. Traditional quantum mechanics suggests that an observer somehow influences the universe by collapsing quantum possibilities into a single reality. The many worlds approach eliminates this need, suggesting that reality simply evolves naturally, without requiring the act of observation to change anything. Instead of the universe selecting a single outcome, all outcomes exist, but in separate worlds. However, this interpretation raises a major question. If multiple versions of reality exist, why do we only experience one? The answer lies in something called decoherence. Quantum superpositions are fragile, and when a system interacts with its environment, it loses its quantum nature and becomes classical in behavior. This process of decoherence ensures that each branch of reality remains separate, meaning we can never cross into another version of events. Even if other versions of ourselves exist in parallel universes, we have no way of perceiving or interacting with them. Despite its strange implications, many worlds is a legitimate scientific hypothesis, considered by some physicists to be the best explanation for quantum mechanics. Some researchers are even looking for ways to test it. One idea involves quantum computing. Quantum computers rely on the ability of particles to exist in multiple states simultaneously. If many worlds is correct, it could mean that quantum computations are actually being performed across multiple parallel universes, with each universe handling a part of the calculation. Some theorists believe that further advances in quantum technology might one day provide indirect evidence for this vast multiverse. If every decision results in the creation of new realities, then does free will truly exist? Every choice is made in some version of reality, meaning there is a universe where you made one decision and another where you made the opposite. Science fiction has explored many worlds through alternate reality stories, parallel universes, and what-if scenarios. From movies and television to literature, the idea that each decision spawns a new reality has fascinated storytellers. In some stories, characters even find ways to interact with alternate versions of themselves, though current physics suggests this is impossible due to decoherence. Some critics argue that the many worlds interpretation is untestable and therefore more of a philosophical idea than a scientific one. Because we cannot communicate between branches of the multiverse, there is no direct way to confirm that these alternate realities exist. Others argue that it introduces an unnecessary complexity, multiplying universes endlessly when a simpler explanation, like wave function collapse, works just as well. Even so, many worlds continues to be taken seriously because it aligns naturally with the mathematics of quantum mechanics. It does not require any hidden variables or unexplained forces. It simply follows from the equations that govern the quantum world. Unlike other interpretations, it provides a fully deterministic view of quantum mechanics, where nothing truly random happens. Every possible outcome occurs somewhere. Decoherence and the observer. How measurement shapes cosmic reality. Why does measurement seem to cause a shift from a range of possible realities to just one? The notion that observation plays a role in determining reality is one of the most debated aspects of quantum physics. Some interpretations suggest that conscious observation is necessary for a quantum state to collapse into a definite outcome. Most, however, believe that decoherence provides an alternative explanation. Instead of requiring a conscious observer, decoherence describes how interactions with the surrounding environment naturally cause quantum systems to behave in classical ways. When a quantum system interacts with countless particles, such as air molecules, photons, or even larger objects, its superpositions become entangled with the environment, effectively destroying their quantum nature. This process rapidly eliminates the possibility of multiple outcomes existing together, making the system appear as if it has chosen a single reality. Decoherence helps explain why large-scale objects do not exhibit the same bizarre behavior as subatomic particles. While an individual electron can exist in multiple places at once, a football or a planet does not. The reason is that larger objects interact with their environment so frequently that any quantum effects become undetectable almost instantly. Even a single photon bouncing off an object is enough to cause decoherence, forcing it into a single, classical state. This is why we do not see superpositions in the everyday world. Quantum uncertainty is constantly being washed away by interactions with the environment. The early universe was a highly quantum system, filled with fluctuations and probabilities at microscopic scales. As the universe expanded and cooled, these quantum effects became locked into place through decoherence, forming the classical structures we see today. Tiny quantum fluctuations in the early universe are believed to have seeded the formation of galaxies, creating the vast cosmic web that stretches across space. Without decoherence, these fluctuations might have remained in a state of superposition, leading to a universe that looked very different, or perhaps one where classical reality never fully emerged. The role of the observer in this process is still a matter of debate. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that observation plays a fundamental role in determining reality. In this view, the act of measurement is what transforms potentialities into actualities. However, decoherence suggests that observation is not strictly necessary. Rather, interactions with the environment serve as a kind of automatic observer, forcing systems into definite states. This means that the classical world as we experience it emerges naturally from quantum mechanics, without requiring a conscious mind to choose an outcome. Yet some physicists argue that decoherence alone does not fully solve the measurement problem. While it explains how superpositions disappear, it does not explain why we observe a specific outcome rather than others. In other words, even if decoherence removes the possibility of quantum states existing in multiple forms simultaneously, it does not explain why one particular reality is chosen over another. This is where interpretations, such as the many worlds interpretation, offer an alternative. If the universe started in a quantum state, then its earliest moments may have contained countless potential versions of its future. Through decoherence, one path was selected, our path. This raises the question of whether other branches of reality exist where the universe evolved differently, shaped by different quantum choices. While these alternate histories remain beyond our reach, their existence cannot be ruled out by current physics. Some physicists are exploring ways to test the effects of decoherence in controlled experiments. Researchers are investigating whether decoherence can be minimized or controlled, potentially offering insights into how classical reality emerges from quantum rules. If decoherence can be slowed down or manipulated, it may provide a deeper understanding of why certain realities unfold while others fade away. Emergent physical laws, order arising from quantum chaos. In the earliest moments of the universe, everything was in an extreme state. Instead of a set framework of laws, the universe may have been governed by randomness, where different regions followed different temporary rules. Over time, as the universe expanded and cooled, patterns could have stabilized, forming the consistent physical laws we observe today. This idea is connected to a broader concept in physics called emergence, the idea that complex systems can produce stable, predictable behavior from underlying chaos. A familiar example of this comes from everyday materials. A cup of water, for instance, follows predictable physical properties. It flows, fills a container, and evaporates at a specific temperature. But on the atomic level, water is made up of countless molecules moving in chaotic, unpredictable ways. The laws governing these individual molecules are not the same as the ones that describe the overall behavior of water. The larger, stable patterns emerge only when many molecules interact over time. Some physicists believe that the laws of the universe could have emerged in a similar way. At the quantum scale, reality is filled with uncertainty. Particles exist in states of probability rather than definite locations. Space itself might fluctuate, appearing and disappearing in brief random bursts. But as the universe expanded, certain patterns may have become dominant, just as stable shapes emerge in chaotic weather systems. The laws of physics could have solidified as a kind of cosmic habit, forming over time as the universe settled into a stable structure. One way to explore this idea is through random matrix theory, a branch of mathematics originally developed to study large, unpredictable systems. When first introduced, it was used to describe the complex energy levels of atomic nuclei. But physicists have discovered that similar mathematical structures appear in quantum gravity, black holes, and even the distribution of prime numbers. This suggests that order might naturally emerge from chaos in fundamental ways, even in the laws that govern the universe. Some theories suggest that, at the very beginning, many different laws could have existed across different regions of space. Only the ones that allowed for stable structures like atoms, stars, and galaxies persisted. If certain physical constants had been different, those regions might have collapsed back into quantum chaos. The laws we observe today could simply be the result of a natural selection process on a cosmic scale, where only self-consistent rules survived. This idea extends to gravity itself. Traditional physics treats gravity as a fundamental force, one of the four interactions that shape the universe. But some researchers argue that gravity might not be a force in the same way as electromagnetism or the strong nuclear force. Instead, it could be an emergent property of spacetime, arising from the collective behavior of countless microscopic quantum interactions. If the laws of physics emerged from an underlying quantum landscape, it is possible that they could shift under extreme conditions, such as near black holes or in the deep past of the universe. Some theories even suggest that in the very distant future, as the universe continues expanding, new physical laws might emerge. The idea that order can arise from chaos is not limited to physics. In biology, complex life forms emerge from simple chemical reactions. In economics, stable markets form from countless unpredictable individual transactions. The same principles may be at work in the fundamental structure of reality. Rather than being dictated by an eternal set of laws, the universe may be shaped by a deeper, evolving process, one where physical rules emerge naturally from an underlying quantum haze. Topology in the pre-cosmic state, the shape of nothingness. Topology is the study of shapes and how they are connected. In everyday life, it helps define objects not by their exact measurements, but by their fundamental properties. A coffee cup, for example, can be stretched or squished into the shape of a donut without breaking or tearing, since both objects have a single hole. But a sphere, which has no holes, is topologically different. In physics, topology plays a key role in understanding how space itself can be curved, connected, or twisted in ways that influence how matter and energy behave. Some think that the pre-Big Bang universe might have had a highly connected, multi-dimensional topology. This means space could have been interwoven in ways that are difficult to visualize in 3 dimensions. Some theories suggest that instead of an infinitely dense point, the universe might have been shaped like a higher dimensional torus, a structure similar to a donut, but with additional dimensions folded in. In such a scenario, space could have been finite but unbounded, meaning it had no clear center or edges, yet it was still a closed system. Another possibility is that the early universe contained wormhole-like structures, tiny tunnels that connected different regions of space. These structures could have allowed quantum fluctuations to interact across vast distances, even before the Big Bang occurred. If such connections existed, they might have influenced how the universe expanded. Some speculate that these wormhole-like topologies could still exist at microscopic scales, hidden within the fabric of space itself. In quantum gravity models, space at the smallest scales is not smooth but highly dynamic, fluctuating between different configurations. This is sometimes described as quantum foam, where spacetime is a seething landscape of constantly forming and dissolving loops. These fluctuations could have played a role in shaping the universe's early topology, influencing how it transitioned from a chaotic pre-Big Bang state into the more orderly expansion that followed. The presence of these loops, or folds, might explain why space expanded the way it did, rather than spreading out uniformly in all directions. String theory also provides a framework for understanding how topology might have influenced the birth of the universe. Some versions of string theory suggest that space could have been curled up in complex ways, and when certain topological features changed, perhaps through a kind of phase transition, the rapid inflationary expansion of the universe could have been triggered. Some researchers propose that changes in the topology of the pre-Big Bang state might have determined the fundamental properties of our universe, such as the number of spatial dimensions. If the fabric of space had different possible configurations before the Big Bang, then only certain topologies may have been stable enough to persist. Mathematical models also suggest that topology changes can occur in extreme conditions, such as inside black holes or during high-energy particle interactions. If similar processes occurred before the Big Bang, then space itself might have undergone transitions where its connectivity changed. This could mean that the universe had previous phases, each with different topological properties. Some theories suggest that certain topological structures, such as extra-dimensional loops or twisted spaces, might store energy in ways that resemble the effects of dark matter or dark energy. If these structures formed before the Big Bang and persisted afterward, they might explain why the universe is expanding at an accelerating rate, or why galaxies rotate in ways that do not match visible matter alone. Thermodynamics of the primordial void, entropy, and the arrow of time. One of the biggest mysteries in cosmology is the origin of time itself. Unlike space, which can be navigated in any direction, time flows in only one direction, always forward, never backward. This progression is known as the arrow of time, and it has a deep connection to thermodynamics, the branch of physics that deals with heat, energy, and entropy. Entropy is a key concept in thermodynamics. It measures the amount of disorder or randomness in a system. In a closed system, entropy tends to increase over time, leading to a gradual shift from order to disorder. This principle explains why a hot cup of coffee left in a room will cool down rather than heat up, why buildings eventually crumble, and why living things age. The universe itself follows this rule. Over time, it moves toward greater disorder, with energy spreading out and becoming less useful. If entropy governs the direction of time in today's universe, it likely played a fundamental role in the earliest moments of existence. What was the entropy of the primordial void, the state that preceded the Big Bang? If the universe began in a highly ordered state with low entropy, then time's forward direction could be a direct result of that initial condition. In standard cosmology, the Big Bang is often thought of as extremely hot and dense. But paradoxically, from a thermodynamic perspective, this state appears to have had very low entropy. Despite the incredible density and energy, the early universe was smooth and uniform, with matter and radiation evenly distributed. This smoothness is puzzling because, statistically, a disordered high-entropy state would be far more likely. Yet, for reasons still not fully understood, the universe started in a condition of extraordinarily low entropy, which then set the stage for everything that followed. One possible explanation is that the primordial void, the nothingness that preceded the Big Bang, was itself a state of even lower entropy. If the void contained no particles, no radiation, and no fluctuations, then it would have represented the ultimate state of order. The moment the universe came into existence, it would have introduced energy and structure, creating the first opportunity for entropy to increase. In this way, time's arrow may have been set in motion at the very moment of cosmic birth, with entropy naturally increasing from that point forward. If a sufficiently large quantum fluctuation occurred, it could have destabilized the vacuum and led to the formation of the universe as we know it. In this scenario, the initial vacuum state would have had lower entropy than the universe that emerged from it, naturally creating a thermodynamic arrow of time. Black holes are known to have extremely high entropy, proportional to the surface area of their event horizons. Some researchers propose that the early universe, rather than being a singular point, could have been more like a white hole, the theoretical opposite of a black hole. A white hole would expel matter and radiation rather than pulling it in, effectively acting as an entropy-reversing explosion. If the Big Bang behaved like a white hole, it could have begun with low entropy and then evolved naturally toward increasing disorder. Some cosmologists suggest that the arrow of time may be an emergent feature. In this view, time does not flow forward inherently, but rather because the conditions of the early universe made it overwhelmingly likely that entropy would increase. If the initial state had been different, if the early universe had been highly disordered instead of smooth and structured, time might have behaved in a completely different way. As the universe grows larger, space stretches, energy spreads out, and complexity increases. This ongoing process of expansion might be driving time forward, ensuring that entropy continues to rise. If this is true, then the arrow of time is tied not just to entropy, but also to the very structure of the cosmos itself. There are also theories that suggest time could flow in multiple directions. Some models propose that, in a sufficiently large multiverse, there could be regions where time runs in reverse relative to our own universe. In these hypothetical universes, entropy would decrease instead of increase, and what we perceive as the future might be another universe's past. If this idea is correct, then the direction of time might not be an absolute feature of reality, but something that depends on the specific conditions of each individual universe. If entropy continues to rise, then the universe will eventually reach a state known as heat death, a time when all energy is evenly distributed and no useful work can be done. In this far future scenario, galaxies will drift apart, stars will burn out, and even black holes will evaporate through Hawking radiation. The universe will become a cold, empty expanse of near-total disorder. If time is defined by the increase of entropy, then in this final state, the arrow of time may cease to have any meaning. The connection between entropy and time suggests that the universe's birth, evolution, and ultimate fate are all part of the same thermodynamic process. If the primordial void had an even lower entropy state than the early universe, then the emergence of time itself may have been an inevitable consequence of that transition. This perspective transforms the Big Bang from a simple explosion into something more like a phase shift. A shift from one state of order to another, with entropy increasing as a natural byproduct. Quantum tunneling, leaping from nothing into existence. In the classical world, objects follow clear-cut rules. A ball rolling toward a hill will either have enough energy to climb over it or it won't. There is no in-between. But in the quantum world, particles do not behave like tiny billiard balls. Instead, they exist as waves of probability, spreading out and interacting. Because of this, a particle encountering a barrier doesn't just stop or bounce back. It has a chance of appearing on the other side, even if it doesn't have enough energy to cross it by conventional means. This is quantum tunneling. In everyday life, quantum tunneling plays a crucial role in many processes. It is essential for nuclear fusion inside stars, allowing protons to overcome their natural repulsion and fuse together, powering the Sun and other stars. It also plays a role in modern technology, from the scanning tunneling microscope, which images surfaces at the atomic scale, to transistors in computers, which rely on quantum effects to function. If the universe emerged from a state of nothingness, then quantum tunneling might have been the key that allowed it to break free from that initial void. If the universe were initially in a state of nothingness, it could have been trapped in a kind of unstable equilibrium. Like a particle in a shallow energy well, it might not have had a clear path to transition into a new state through classical means. However, just as a particle can tunnel through a barrier that it couldn't otherwise cross, the universe itself might have quantum tunneled from this initial state into an expanding, evolving cosmos. This process is sometimes referred to as quantum cosmogenesis, where the laws of quantum mechanics, rather than classical determinism, dictate the birth of the universe. One of the most well-known models incorporating this idea comes from physicist Alexander Vilenkin. In his model, spacetime itself is treated as a quantum system. Just as an electron can tunnel through a potential barrier, the entire universe could have tunneled out of a state where no space, time, or matter existed, emerging as a rapidly expanding entity. This idea suggests that even if there was no classical cause for the universe's beginning, quantum mechanics provides a pathway for something to emerge from apparent nothingness. This means that in some sense, the existence of the universe is not a violation of physical principles, but a natural consequence of how quantum systems behave. Given that particles constantly pop in and out of existence on the quantum scale, an entire universe appearing through a similar process may not be as strange as it seems. If quantum tunneling can create a universe from an unstable vacuum state, then it could, in principle, happen more than once. This leads to scenarios where multiple universes exist in parallel, each having tunneled into existence through similar quantum processes. The challenge with this idea is that while it is mathematically plausible, direct experimental evidence is difficult to obtain. The universe's birth happened on timescales and energy levels far beyond what we can currently observe. Trans-planckian considerations beyond the edge of known physics. At the smallest scales imaginable, deep beyond the reach of current experiments, the nature of reality itself becomes uncertain. The Planck scale, defined by minuscule units of length, time, and energy, marks the boundary at which the known laws of physics lose their reliability. At this scale, space and time no longer behave in ways that can be described by general relativity or quantum mechanics alone. Instead, something more fundamental is at play, something beyond the reach of our current understanding. This is the domain of Trans-planckian physics. The Planck length, approximately 1.6 to the power of -35 meters, represents a scale so small that even the most advanced particle accelerators could never directly probe it. This length is many orders of magnitude smaller than the nucleus of an atom. At this scale, quantum fluctuations in spacetime are predicted to become so extreme that the very fabric of reality would appear to shift and ripple unpredictably. One of the biggest challenges in understanding Trans-planckian physics is that traditional tools of measurement cease to function. In normal physics, energy and distance are linked. To probe smaller and smaller scales, scientists use higher and higher energy collisions, as in particle accelerators. However, at the Planck scale, the energy required to examine such small distances becomes so extreme that it would collapse into a black hole before any meaningful observation could be made. This paradox suggests that the very concept of measuring space at this level might be flawed. One potential avenue for exploring Trans-planckian physics is through the study of high-energy cosmic rays. These particles, which travel across the universe at nearly the speed of light, sometimes carry energies far beyond what our particle accelerators can produce. If these extreme particles interact in ways that differ from predictions based on standard physics, they could offer hints about what happens at scales beyond our current understanding. There is also the possibility that new experiments in quantum optics and condensed matter physics could provide insights. Some researchers have proposed analogues of Trans-planckian effects in laboratory settings, using systems where the behavior of quantum fluids or exotic materials mimics the way spacetime might behave near the Planck scale. While these experiments cannot directly probe the fundamental nature of reality, they could offer clues about how physics operates when conventional assumptions break down. The search for Trans-planckian physics is a search for the foundations of reality itself. Whether the key lies in string theory, quantum loops, or yet undiscovered principles, one thing is clear. The Planck scale is not the end of the road, but a gateway to deeper mysteries. What lies beyond it could redefine our understanding of the cosmos, space, time, and the very nature of existence. Symmetry versus asymmetry, the dual forces in early universe dynamics. In the earliest moments of the universe, forces, particles, and space itself were bound together in a state of near-perfect symmetry. Everything was uniform, balanced, and indistinguishable from anything else. But as the universe expanded and cooled, this symmetry began to break, giving rise to the complex, structured cosmos we see today. Symmetry in physics is a concept that describes a system's invariance under a transformation. If an object or a system looks the same after undergoing a specific change, such as rotation, reflection, or translation, it is said to have symmetry. In the context of the early universe, symmetry meant that all fundamental forces and particles were unified. Matter and antimatter were in perfect balance, and there was no clear differentiation between the particles that would later become protons, neutrons, and electrons. This state of near-perfect symmetry could not last indefinitely. As the universe expanded and its temperature dropped, symmetry-breaking events occurred. When symmetry breaks, previously identical elements begin to diverge, creating structure and complexity where none existed before. This is what allowed particles to acquire mass, forces to separate, and the cosmos to become the intricate system we observe today. One of the most significant examples of symmetry breaking in the early universe is known as spontaneous symmetry breaking. In this process, a system that initially follows a symmetrical pattern naturally shifts into a less symmetrical state due to underlying dynamics. First, gravity split off, becoming a distinct force that shaped the large-scale structure of the cosmos. Then, the strong nuclear force separated from the electroweak force, allowing protons and neutrons to form. Eventually, the weak nuclear force and electromagnetism split, finalizing the four fundamental forces we recognize today. In the earliest universe, particles moved as if they had no mass, interacting in a way that maintained perfect symmetry. However, as the universe cooled, the Higgs field, a field that permeates all of space, underwent a phase transition. This transition created an asymmetry, causing some particles to interact with the Higgs field more strongly than others, acquiring mass in the process. This breaking of symmetry was essential in forming the stable matter that would go on to build atoms, stars, and galaxies. According to our best understanding, the Big Bang should have created equal amounts of matter and antimatter. However, if that had happened, the two would have annihilated each other completely, leaving behind a universe filled only with radiation. Instead, for reasons not yet fully understood, a slight asymmetry arose, leading to an excess of matter over antimatter. This tiny imbalance, possibly as little as one extra particle of matter for every billion particles of antimatter, was enough to allow the formation of all the galaxies, stars, and planets we see today. Some theories suggest that time might have emerged from a form of symmetry breaking. In the earliest universe, time may have been indistinguishable from space, forming a four-dimensional continuum where no single direction of time existed. But as the universe evolved, time took on a distinct forward direction, driven by the thermodynamic arrow of time, which is closely tied to the increase of entropy. Even in modern physics, researchers continue to explore deeper layers of symmetry that might exist at scales we have yet to probe. Supersymmetry, a proposed extension of the standard model of particle physics, suggests that every known particle has an undiscovered superpartner, restoring a deeper symmetry that might have existed in the early universe. While no direct evidence for supersymmetry has been found, it remains one of the most promising candidates for explaining the mysteries of dark matter and unifying the fundamental forces. The world we observe is the result of finely tuned imbalances, where perfect symmetry would have left a barren, lifeless void. Instead, the universe thrives on its imperfections. The formation of atoms, the structure of galaxies, and even the conditions for life itself depend on slight deviations from absolute symmetry. Dark energy's precursor role influences on the initial expansion. When astronomers look out into the cosmos, they see galaxies moving away from each other, as if space itself is stretching. This discovery, first observed by Edwin Hubble in the early 20th century, led to the idea that the universe was once much smaller and has been expanding ever since. But in the late 1990s, scientists discovered something unexpected. Not only is the universe expanding, but this expansion is actually accelerating. While dark energy is often discussed in the context of the present-day universe, some scientists have begun to wonder whether a force similar to dark energy played a role in the very earliest moments of cosmic history. Instead of a simple, uniform expansion, the early universe might have been shaped by an invisible force that influenced the rate and structure of cosmic growth, before forces like gravity and electromagnetism became dominant. To explore this idea, it is important to understand what dark energy is, or at least what scientists believe it might be. Unlike normal matter and energy, which interact through forces such as gravity and electromagnetism, dark energy seems to act in opposition to gravity. Instead of pulling things together, it pushes space apart, causing galaxies to separate at an accelerating rate. The most widely accepted explanation is that dark energy is linked to vacuum energy. In this view, a vacuum has a small but constant energy density that exerts a repulsive force on the cosmos. The true cause of inflation remains unknown, and some researchers suspect that a force resembling dark energy may have been responsible. One possibility is that an early form of dark energy acted as an inflaton field, a theoretical energy field that fueled inflation. In this scenario, the inflaton field filled the universe with a kind of vacuum energy, causing space to expand exponentially. Once inflation ended, the energy from this field would have decayed into the particles and radiation that make up the universe today. If this idea is correct, dark energy and inflation might be two sides of the same coin. Another idea is that dark energy-like effects were present even before inflation. In this view, a force similar to dark energy might have played a role in lifting the universe out of this unstable vacuum, setting off a chain reaction that led to inflation. Today, dark energy dominates over gravity on the largest cosmic scales, pushing galaxies apart. But in the early universe, before ordinary matter had begun to form stars and galaxies, a similar force could have played a role in determining the distribution of matter. If this effect existed, it could have left subtle imprints on the arrangement of galaxies, which astronomers might be able to detect by analyzing the cosmic web. One of the biggest challenges in studying early dark energy is finding evidence for it. Unlike ordinary matter, which can be observed through telescopes, dark energy does not emit or absorb light, making it incredibly difficult to detect. However, there are a few indirect methods that scientists can use to search for clues. By studying tiny fluctuations in the CMB, researchers can learn more about the conditions that existed in the early universe. Another potential avenue of investigation is the large-scale structure of the universe itself. If early dark energy played a role in shaping cosmic expansion, it could have influenced the way galaxies and clusters of galaxies formed over billions of years. By mapping the distribution of galaxies across different cosmic epochs, scientists may be able to detect patterns that point to an early period of dark energy-driven expansion. Experiments involving gravitational waves could also provide new insights. If early dark energy had an effect on the fabric of spacetime, it might have influenced the propagation of these waves, creating distortions that could be observed with highly sensitive detectors. If such a force did exist, instead of being a passive stage on which cosmic events unfolded, spacetime may have been a dynamic, evolving entity with energy fields and forces that operated in strange ways. Exotic matter and early cosmic expansion beyond ordinary physics. When scientists talk about exotic matter, they are referring to substances that behave in ways unlike anything we typically encounter. These are not your standard protons, neutrons, and electrons. Instead, exotic matter might possess peculiar properties that could be linked to phenomena such as negative energy, negative mass, or bizarre quantum states. It is possible that such substances could have been crucial in the birth of the cosmos and might even hold the key to understanding the forces that shaped its initial expansion. While the nature of the inflaton field remains uncertain, some scientists speculate that it could have been a form of exotic matter. The inflaton field might have been made up of particles or fields with strange properties that allowed the universe to grow exponentially in a very short period. These particles or fields would have had the ability to store vast amounts of energy, which then released as the universe expanded. One idea is that this exotic matter might have exhibited a negative pressure, a property that would have led to an accelerated expansion. In contrast to the attractive force of gravity, which pulls things together, negative pressure would have acted like a repulsive force, pushing space apart. This is similar to how dark energy works today, although in the early universe, the forces involved might have been much stronger and more chaotic. This form of matter would not behave like ordinary matter in a gravitational field, and could even have played a role in stabilizing the rapid expansion of the universe during the inflationary epoch. Exotic matter could also have played a role in how the universe transitioned from an inflationary phase to the hot, dense state that marked the beginning of the Big Bang proper. As inflation ended, the energy from the exotic matter would have decayed into particles and radiation, setting off the conditions for the formation of the first atoms, stars, and galaxies. The interactions between these unusual forms of matter and ordinary matter would have shaped the fundamental properties of the universe, such as its temperature, density, and the distribution of energy. As the universe cooled and began to expand, matter started to clump together under the influence of gravity. But what if exotic forms of matter played a role in guiding how these structures formed? For example, some suggest that exotic matter might have created regions of space with unusual properties, places where the density and temperature were higher or lower than the surrounding areas. These regions could have acted like seeds for the formation of cosmic structures, giving rise to galaxies and clusters of galaxies in patterns that might have been influenced by the presence of this exotic material. The way in which these early regions of high or low energy density evolved could have set the stage for the cosmic web that connects galaxies across vast stretches of space. Negative mass is a theoretical form of matter that would behave in a radically different way from ordinary matter. Instead of attracting other objects via gravity, negative mass would repel them. If negative mass existed in the early universe, it could have had profound implications for cosmic expansion. It might have acted as a counterforce to gravity, helping to drive the rapid expansion during the inflationary period, and potentially influencing the formation of large-scale structures in the universe. While its existence has yet to be observed in nature, there are theoretical reasons to believe that it might exist under certain conditions. Certain solutions to equations in general relativity suggest that negative mass could emerge in specific environments, such as within certain kinds of exotic energy fields, or in the presence of very high energy conditions. The challenge for scientists is to figure out whether such conditions could have occurred in the early universe. Despite the speculation, many of these ideas remain unproven. The challenge lies in the fact that these forms of matter do not interact with light in the same way that ordinary matter does, making them incredibly difficult to detect. Additionally, the extreme conditions of the early universe make it challenging to recreate or study these substances in a controlled laboratory environment. The algorithmic universe, cosmic computation, and simulated beginnings. What if the universe itself operates like a vast computational system? This perspective doesn't necessarily mean the universe is a literal computer in the way we understand them, but rather that the fundamental processes of reality could be described in algorithmic terms. The rules governing physics might function like lines of code, shaping the behavior of space, time, and matter according to a deep, underlying logic. If this is true, the universe may not just be governed by mathematics, it may, in some sense, be a computational construct. One of the earliest hints that nature might work like a computation comes from the way physical laws seem to be built on fundamental bits of information. In physics, information isn't just an abstract concept, it has real physical meaning. In the 20th century, scientists discovered that quantum mechanics places strict limits on how much information can be known about a system. The famous uncertainty principle, for example, suggests that there are constraints on how precisely we can measure certain properties of particles. Some researchers have gone further, proposing that space and time themselves could emerge from information processing at the smallest scales. One of the key figures in this field, physicist John Archibald Wheeler, suggested the idea of it from bit, the notion that physical reality arises from informational building blocks. In this view, the universe isn't fundamentally made of particles or waves, but of information that is processed according to deep, underlying rules. Just as computer programs execute instructions to generate complex outputs, The universe may follow a set of rules that give rise to everything we observe. Quantum mechanics adds an interesting twist to this idea. When we observe a quantum system, its state seems to snap into place, as if it had been undecided until the moment of measurement. Some interpretations suggest that reality doesn't exist in a well-defined way until it is observed, similar to how a computer program only renders parts of a digital world when a player moves through it in a video game. If this is the case, the universe could be running on an underlying computational process that only renders reality as needed. A related idea comes from cellular automata, mathematical systems that follow simple rules to generate complex patterns. In the 20th century, mathematician John Conway created a system called the game of life, where a grid of cells changes over time based on a few straightforward rules. Although the system is incredibly simple, it can generate highly complex behavior, including self-replicating patterns that resemble living organisms. Some physicists wonder if the universe operates in a similar way, if simple underlying rules at the smallest scales might give rise to the complexity of galaxies, stars, and even life. In the realm of theoretical physics, some researchers have explored the possibility that the fabric of reality is a kind of computational lattice. The idea is that space and time might not be continuous, but instead be made up of tiny, discrete units, like pixels on a screen. These fundamental units, sometimes called Planck-scale voxels or quantum bits, qubits, would interact according to computational principles, evolving in a way that gives rise to the large-scale structures we see in the cosmos. One of the more radical versions of this idea is the simulation hypothesis, which suggests that the entire universe might be a simulated reality running on an advanced form of computation. This concept, popularized by philosopher Nick Bostrom, proposes that a civilization advanced enough to simulate entire worlds could create artificial universes indistinguishable from the real thing. If this were possible, and if such civilizations created many simulations, then the odds might suggest that we ourselves are living in one rather than in the base-level reality. While this idea remains highly speculative, it has intrigued thinkers across multiple fields, including physics, computer science, and philosophy. People have looked for ways to test whether the universe has features of a simulation. One possible clue could come from studying the limits of information storage in the universe. In conventional physics, the Bekenstein bound sets an upper limit on the amount of information that can be contained within a given region of space. If spacetime were a kind of computational structure, there might be subtle signs that reality has a finite resolution, much like how digital images reveal pixelation when magnified. Some have suggested that if the universe were a simulation, there might be detectable anomalies in particle physics, such as unexpected energy limits or patterns in cosmic rays, that could suggest an underlying computational framework. So far, no such evidence has emerged. If reality operates like an algorithm, who or what set the rules? Are they the result of fundamental necessity, meaning that the laws of physics are the only ones that could exist? Or could there be other possible sets of rules, leading to entirely different kinds of universes? Even if the universe is not a programmed simulation, the rules governing physics may naturally lead to the emergence of higher-order structures. In the same way that simple laws in physics can lead to complex weather patterns or biological evolution, the fundamental principles of the universe might inherently drive the formation of galaxies, black holes, and ultimately conscious beings capable of questioning their own origins. As research in this field continues, new technologies may offer insights into the computational nature of reality. Advances in quantum computing could allow physicists to simulate aspects of the early universe, potentially revealing how complex systems emerge from simple rules. Developments in artificial intelligence might also help researchers uncover hidden patterns in physical law, pointing towards deeper principles that govern space and time. If the universe follows deep algorithmic rules, then mastering those rules could give rise to new ways of manipulating matter and energy. This could lead to breakthroughs in fields like quantum engineering, space travel, or even understanding consciousness. cosmic strings, and the fabric of reality, weaving hidden dimensions. To understand cosmic strings, it's helpful to first think about the structure of spacetime. In the simplest terms, spacetime is the fabric that supports everything in the universe: planets, stars, galaxies, and even light. This fabric is not uniform. It can bend, twist, and warp in response to matter and energy. The theory of general relativity describes this dynamic behavior, showing how massive objects like stars and black holes warp spacetime around them. Now, imagine that during the early stages of the universe, the fabric of spacetime wasn't perfectly smooth. Instead, just as defects can form in any material, like cracks in a glass or imperfections in metal, spacetime could have undergone similar disturbances. These disturbances, if they happened, might have created cosmic strings, long, thin, and incredibly dense objects stretching across the universe, with one-dimensional defects at their core. Cosmic strings would be fundamentally different from the familiar objects in our universe. They wouldn't be made up of normal matter, like atoms or molecules, but rather would be defects in space-time itself. They would be extremely thin, perhaps as narrow as a single atom in diameter, but potentially stretching for thousands or even millions of light years in length. In other words, these cosmic strings could be vast, stretching across the universe in ways that might dwarf even the most enormous galaxies. These strings might not be easily visible, but they would leave their mark on the surrounding space-time. For instance, their enormous mass and energy would cause nearby space-time to warp, affecting the trajectories of nearby stars and even light. This could make them detectable, at least indirectly, through their gravitational effects on their surroundings. According to some theories, inflation could have created these strings as a byproduct. In these models, the universe's expansion wasn't smooth and continuous, but rather marked by rapid fluctuations in the space-time fabric. These fluctuations could have caused cosmic strings to form as the universe cooled and settled into its present structure. One of the key features of cosmic strings is that they could act as a sort of scaffold for the universe's structure. Just as a crack in a solid material can influence how stress is distributed across the material, a cosmic string could influence the distribution of matter and energy in its vicinity. Their gravitational effects could have helped guide the formation of galaxies, clusters of galaxies, and other large-scale structures in the universe. In fact, some scientists have suggested that cosmic strings could be responsible for some of the cosmic web we see today, the vast network of filaments and voids that make up the large-scale structure of the universe. The idea is that these cosmic strings might have acted as gravitational seeds that drew matter together, encouraging the formation of galaxies and galaxy clusters in their wake. Their existence would suggest that space-time is not just a passive background for events to unfold, but an active, dynamic medium capable of having defects and structures of its own. This idea resonates with other theories that challenge our conventional understanding of space-time, such as the notion that space-time itself might be a kind of computational fabric, constantly written and updated according to deep underlying rules. Cosmic strings may provide hints about the relationship between higher dimensions and our observable universe. Some theories of string theory and higher dimensional physics propose that extra dimensions could be compactified. Cosmic strings might be one manifestation of these hidden dimensions. Cosmic strings are predicted to have very specific characteristics that could potentially be detectable through observation. Gravitational lensing occurs when massive objects bend light as it passes by, distorting the images of objects behind them. Cosmic strings, with their incredibly dense and stretched-out nature, could have similar effects, bending light in a way that would be detectable by telescopes. In some cases, the bending could create unusual visual effects, such as multiple images of the same object, or even Einstein rings, circular patterns formed by light bending around the string. No direct evidence of cosmic strings has been found so far. Their detection is an ongoing challenge, both because of their subtle effects on the surrounding space and because they may be incredibly rare or even absent in our region of the universe. Yet the very idea that such structures could exist forces us to reconsider how we think about space-time. Symbiotic cosmology, co-creation of space-time and quantum fields. The concept of symbiotic cosmology proposes that space-time and quantum fields did not emerge independently, but rather evolved in a mutually dependent relationship. Instead of space-time emerging first, followed by the fields and particles that populate it, this theory suggests that the two could have co-evolved together, shaping one another in a continuous, interconnected process. Quantum fields, the fundamental building blocks of all particles, may not have simply filled a pre-existing space-time. This model suggests that the universe did not begin with a static, dimensionless point of space, nor did it unfold in a simple sequence of events where one structure appeared before another. The earliest moments of the universe were likely governed by quantum phenomena, where particles and fields were in a state of constant fluctuation, existing in a state of uncertainty. This is a period in which the usual understanding of space-time as a continuous, smooth structure breaks down and quantum effects dominate. In this context, symbiotic cosmology suggests that space-time itself was not just the backdrop against which quantum processes unfolded. The properties of space-time, such as its curvature, its expansion, and its density, could have evolved alongside the quantum fields that drive the interactions of particles. Each quantum fluctuation could have contributed not only to the creation of matter, but also to the curvature and expansion of space itself, forming an interconnected feedback loop that drove the birth of the universe. The intricate relationship between space-time and quantum fields could have been responsible for setting the rules that govern the development of the universe. The way that space-time expanded, the way that matter began to condense, and the way that forces emerged. Each of these processes could have been influenced by the intertwined evolution of both space-time and quantum fields. This makes the early universe a far more dynamic and complex environment than what is typically imagined in the standard cosmological models. Quantum fields permeate all of space, shaping the behavior of matter and energy. In the symbiotic model, these quantum fields would not only define the properties of particles, but they would actively contribute to the formation of space-time. The fields themselves could be seen as emerging from a deeper underlying structure, perhaps one that is completely non-spatial or that transcends the conventional dimensions we observe. This would mean that space-time and quantum fields are not independent entities, but rather two aspects of a single unified process of creation. In the early universe, space-time could have been far more dynamic and mutable, shaped by the interactions of quantum fields and particles. As the universe expanded, these quantum fields could have influenced how space-time unfolded, leading to the universe we experience today. Time loops and cosmic recurrence, cycles beyond the Big Bang. The notion of cyclic universes is not entirely new. Ancient philosophies, including those from India and Greece, have explored the idea of recurring worlds and eternal returns. However, modern physics is now revisiting these ideas through the lens of cosmology, applying them to the observable universe. The most well-known cyclic model is the Big Bounce scenario, where instead of a singular Big Bang, the universe might have undergone a series of expansions and contractions, each followed by a bounce that sets the stage for a new expansion. The bounce occurs when the universe, after contracting to a very dense and hot state, reaches a critical point and rebounds, triggering a new expansion phase. This process could repeat infinitely, with each cycle generating a universe similar to the one that came before it. While we may have experienced one specific phase of the cycle, the universe itself has been cycling through phases of expansion, contraction, and rebirth for eternity. Each cycle may reset the universe, ensuring the right conditions for the formation of galaxies, stars, and life. However, the cyclic model also raises some difficult questions. For instance, how would each cycle begin? And how would it avoid repeating the errors or imbalances of the previous cycle? Would the laws of physics remain constant across cycles, or would they evolve and change over time? One possibility is that each new cycle could be slightly different from the last, with minor changes in the physical constants or the structure of spacetime itself. Alternatively, the cycles might be largely identical, with the same physical laws governing each new iteration of the universe. Another intriguing aspect of the cyclic model is the potential for time loops, circular patterns in the flow of time itself. These loops could provide an elegant explanation for the observed order and symmetry of the cosmos. The laws of physics, as we know them, may be a reflection of this looping structure, allowing for a consistent set of rules to govern each iteration of the universe. One suggestion is that quantum information, the fundamental data that makes up the universe, might be passed from one cycle to the next, allowing information to persist across time loops. This would provide a link between the past and the future, enabling the continuity of the universe from one cycle to the next. Such a mechanism could resolve some of the paradoxes of quantum mechanics, such as the measurement problem and the question of why the universe seems to follow specific rules, despite the apparent randomness of quantum particles. The question of what causes each new cycle to begin is still open to debate. In some versions of cyclic cosmology, the universe's expansion might slow down and eventually reverse itself, causing it to collapse into a singular point before bouncing again. This big crunch, followed by a bounce scenario, is one of the most widely discussed in the context of cyclic models. However, new theories, particularly those based on dark energy, suggest that the universe may continue to expand indefinitely. If the current acceleration in the expansion of the universe caused by dark energy is correct, then a big crunch might not occur. Instead, the universe might keep expanding forever, but in a manner that eventually leads to the decoupling of spacetime, where spacetime itself is stretched out so far that it cannot reconnect in a future bounce. In a universe that undergoes endless cycles, one might wonder how entropy behaves over time. If the universe continually recycles itself, does entropy reset with each cycle, or does it build up over time, making each new iteration more disordered than the last? Some suggest that the laws of thermodynamics might evolve in such a way that entropy doesn't accumulate in the traditional sense, allowing the universe to remain in a state that is conducive to life and complexity. Others believe that the accumulation could eventually limit the number of times the cycle can continue, leading to a final state of the universe, a state in which no further cycles are possible. Future horizons, next-generation experiments, and theoretical advancements. The search for answers about the origins of the universe continues to drive some of the most ambitious scientific projects ever conceived. The future of cosmology will depend not only on theoretical breakthroughs, but also on the development of new observational tools and experiments that push the limits of our current technology. As scientists probe deeper into the nature of space, time, and matter, a new generation of instruments and ideas promises to revolutionize our understanding of the cosmos. From powerful telescopes designed to capture the earliest light of the universe, to high-energy particle experiments that recreate conditions close to the Big Bang, the coming decades hold the potential for transformative discoveries. The James Webb Space Telescope has already provided glimpses of galaxies from the first few 100 million years after the Big Bang, but future space telescopes will look even further back in time. The proposed Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, and the Habitable Worlds Observatory could help refine our understanding of the universe's earlier structures and the transition from the primordial darkness to the first stars. Another major project, the Nancy Grace Roman Space Telescope, will specialize in studying dark energy and the large-scale structure of the cosmos. By mapping the distribution of galaxies across billions of years of cosmic history, these telescopes could offer clues about the fundamental forces that shaped the early universe. Ground-based observatories are also undergoing major upgrades to enhance their ability to detect faint signals from deep space. The upcoming extremely large telescope in Chile, with a massive 39-meter mirror, will provide unprecedented detail when studying distant galaxies, allowing researchers to investigate the physics of early cosmic structures. Meanwhile, radio telescopes like the Square Kilometre Array will survey the sky with incredible sensitivity, potentially detecting faint radiation from the first black holes, and even searching for signals that could hint at new physics beyond the standard model. These observatories will help address lingering questions about inflation, the CMB, and the nature of dark matter. Since the first direct detection of gravitational waves in 2015, observatories like LIGO and Virgo have allowed scientists to study black hole mergers and neutron star collisions. Future detectors, such as the Laser Interferometer Space Antenna, will operate in space and be sensitive to lower frequency gravitational waves, potentially capturing signals from the very early universe. If cosmic inflation produced gravitational waves, as some theories predict, these signals could be imprinted on spacetime itself, offering direct evidence of the universe's earliest moments. Similarly, next-generation ground-based observatories like the Einstein telescope could improve our ability to detect these waves and reveal new insights about the behavior of gravity in extreme conditions. High-energy particle physics will also play a key role in exploring cosmic origins. While the LHC has helped confirm key aspects of the standard model of particle physics, future colliders will push energy levels even further. The proposed Future Circular Collider and the International Linear Collider aim to probe deeper into the nature of fundamental particles and interactions. These machines could provide insights into the Higgs field and test theories that propose extensions to the standard model, such as supersymmetry. If exotic particles related to dark matter or quantum gravity exist, these experiments may be the first to detect them. The idea of quantum simulations is gaining traction as a way to study conditions that would otherwise be impossible to recreate in a laboratory. By using quantum computers to model the behavior of particles in extreme environments, scientists hope to simulate the physics of the early universe. These simulations could offer insights into how quantum fluctuations shaped cosmic inflation, or how spacetime itself may emerge from deeper quantum processes. The rapid progress in quantum computing may soon allow for direct modeling of scenarios that were once purely theoretical. The study of dark energy and dark matter will continue to be one of the most important frontiers in cosmology. Theories suggest that these invisible forces and substances could be tied to undiscovered particles or even modifications of gravity itself. Upcoming experiments like the Euclid mission and the Vera C. Rubin Observatory will aim to map the distribution of dark matter with greater precision, potentially revealing whether it interacts with normal matter in unexpected ways. Meanwhile, laboratory experiments searching for weakly interacting massive particles or axions could provide the first direct evidence of dark matter's existence. If new particles are discovered, they could revolutionize our understanding of the universe's composition and evolution. As technology advances, entirely new methods of observation may emerge. Future telescopes might be able to detect signs of primordial black holes, relics from the earliest moments of the universe that could offer insights into its initial conditions. Experiments involving ultra-cold atoms or high-precision clocks could test whether time and space behave differently under extreme conditions. Even unexpected breakthroughs, such as detecting cosmic signatures of unknown particles or identifying anomalies in the CMB, could point toward new physics waiting to be uncovered. With each new observation and discovery, the frontier of knowledge will expand, bringing us closer to answering some of the most profound questions about the nature of space and time. Comparative cosmology, weighing inflation against alternative theories. At its core, inflation theory addresses the need to explain the uniformity and large-scale structure of the universe. In a standard Big Bang model, the universe would have been full of small, random fluctuations after its initial expansion. However, these fluctuations would have grown over time, and the universe we observe today should have large regions of both matter and empty space that are highly irregular. Inflation would have stretched out any irregularities, while also providing a mechanism for the formation of galaxies and large-scale structures by stretching out small quantum fluctuations into observable variations in the density of matter. Yet, despite these successes, inflation is not without its challenges. One of the main criticisms is that it relies on speculative physics, including the idea of a hypothetical inflaton field. While the inflationary model does offer a solution to several cosmological problems, it also introduces new ones, such as the need to identify the exact nature of this mysterious field and how it behaves over time. The mechanism behind inflation remains an open question, and there is no clear experimental evidence directly supporting the existence of an inflaton field. In contrast, some alternative models propose different mechanisms for explaining the early universe. According to the cyclic universe model, the Big Bang was not the beginning, but rather the latest in a series of bounces, in which the universe expands from a previous contraction. This theory avoids the need for a singular beginning, instead proposing that the universe has been in a state of continual renewal. The cyclic model also offers an explanation for certain observed features of the universe, such as its large-scale homogeneity, by suggesting that each cycle's expansion erases any remnants of the previous cycle's irregularities. One of the key problems with this is the lack of direct observational evidence for previous cycles. The theory also struggles to account for the observed acceleration of the universe's expansion, which would be difficult to explain in a universe that alternates between expansion and contraction. In addition, the cyclic model requires the existence of additional dimensions or new forms of matter, making it a more speculative theory that relies on ideas not yet fully understood. The ekpyrotic model, meanwhile, is rooted in string theory, but the idea of higher dimensional branes and string theory is still highly speculative. String theory itself remains unproven, and the extra dimensions it predicts have not been observed. Furthermore, while the ekpyrotic model can explain the universe's uniformity, it does not provide a satisfactory explanation for the observed distribution of matter and large-scale structures. Without further experimental evidence, it remains a highly theoretical model, though one that is intriguing in its potential to offer new insights into the universe's origins. The steady-state theory, which posits that the universe has always existed in a steady, expanding state, also presents a challenge to inflationary cosmology. According to the steady-state model, new matter is continuously created as the universe expands, maintaining a constant average density. This model was initially proposed to explain why the universe appears largely uniform at large scales, without requiring a Big Bang origin. However, this theory was largely abandoned after the discovery of the CMB, which provided strong evidence for the Big Bang and suggested that the universe had a definite beginning. Despite its rejection by most cosmologists, the steady-state theory still holds appeal for some. Modern variations of the theory suggest that new regions of space could constantly emerge, either through quantum fluctuations or by processes that we do not yet fully understand. According to the multiverse hypothesis, our universe is just one of many, each with its own set of physical laws and constants. While the idea offers an elegant solution to certain cosmological puzzles, it also raises philosophical and scientific challenges. One of the main problems is that the multiverse hypothesis is difficult to test. Since other universes, if they exist, are beyond our observational reach, it is hard to see how the theory can be falsified or validated through experiments. In comparing these alternative theories to the inflationary model, it is clear that each offers its own strengths and weaknesses. Inflation remains the most widely accepted explanation for the early universe due to its ability to solve several major cosmological problems, such as the horizon and flatness problems. The zero-dimension hypothesis. Birth from a dimensionless state. In most cosmological models, space and time are fundamental aspects of existence. We imagine the universe beginning as an incredibly tiny, dense point. But what if this starting point wasn't a point at all? What if, before space and time came into being, there was something entirely different? Something that had no dimensions, no location, and no time? This is the idea behind the zero-dimension hypothesis. In our everyday experience, everything exists somewhere. Objects have length, width, and height, and even in the tiniest scales of quantum mechanics, particles occupy a region of space. But a truly zero-dimensional state would be different. It would have no extension, no size, no inside or outside, just pure potential. This is difficult to imagine because everything we know is embedded within space and time. Yet some physicists and philosophers argue that such a state could have been the ultimate precursor to the universe. One way to think about this is in terms of information. Before the Big Bang, there may not have been a physical entity as we understand it, but there could have been a kind of abstract, mathematical structure, pure information or fundamental laws that existed without needing a spatial container. This would mean that the fabric of reality was initially defined not by physical dimensions, but by relationships between mathematical entities. It's a radical idea, but not entirely without precedent. Modern physics already describes the universe in terms of mathematical structures, with space-time itself emerging as a consequence of deeper underlying principles. Some quantum gravity models explore the idea that space is not fundamental, but emerges from more basic principles. Loop quantum gravity, for instance, suggests that space is made up of discrete units, like tiny building blocks that come together to form the reality we experience. If space is not fundamental, then perhaps there was a stage before these building blocks existed, a state where the concept of space had no meaning. In such a scenario, the early universe would not have had any dimensions at all, only a set of rules or interactions waiting to unfold. Another approach to the zero-dimension hypothesis comes from theoretical physics models that propose a pre-geometric state. Instead of space being a fixed background, it could emerge from something more abstract, such as a network of relationships. Some physicists suggest that reality could have begun as a complex system of interconnected mathematical points, entities that did not yet possess the concept of distance or direction. These points could have transitioned into a three-dimensional universe through a process analogous to phase transitions in physics, where a system undergoes a sudden change in structure. If space and time are emergent rather than fundamental, then their creation could have been a kind of spontaneous transition from a non-spatial state. This aligns with some interpretations of quantum mechanics, where certain properties of particles do not exist until they are measured. Could it be that space itself did not exist until it was, in a sense, measured or realized through the process of cosmic evolution? If so, the universe could have originated from a state where dimensions were not just absent, but entirely meaningless. Some speculative theories suggest that the zero-dimension state might have been a kind of mathematical singularity, not a singularity in the traditional sense of infinite density, but rather a state where all possible realities were condensed into a single, dimensionless point of pure potential. This would mean that the universe didn't expand from a tiny point in space, but from a state where space itself did not yet exist. In this view, the emergence of dimensions would have been akin to the unfolding of information, like a computer program generating a three-dimensional world from a set of underlying rules. One of the challenges of this idea is explaining how something can exist outside of dimensions. Our understanding of physics relies on measurable properties, but if there was a state where measurements had no meaning, then describing that state becomes nearly impossible. Yet, some hints may come from quantum mechanics. In the quantum world, particles exist in a superposition of states until they interact with something that forces them to take on a definite form. Could it be that the early universe existed in a superposition of all possible dimensional states, and that what we see today is just one realized outcome? Some versions of string theory explore the possibility that extra dimensions could have existed in the early universe but later compactified, becoming too small to detect. But what if the opposite were true? What if the universe began with no dimensions at all and expanded into multiple dimensions over time? In such a scenario, the very laws of physics might have evolved alongside the emergence of space itself. Black holes represent regions where space and time break down, and in some extreme cases, the singularity at their core might not be a point in space, but rather a state where the concept of space ceases to be meaningful. If black holes can lead to a breakdown of space, then the early universe might have emerged from a similar breakdown, but in reverse, a process where dimensions were created instead of being destroyed. If space and time emerged from a state of pure potential, could there be other dimensions waiting to unfold? Could the fabric of space be more malleable than we think? And if our universe emerged from a state with no dimensions, could it one day return to such a state in the distant future? Digital ether, information as the fundamental fabric of the cosmos. In classical physics, the ether was once imagined as a medium that filled all of space, serving as a conduit for the propagation of light and other electromagnetic waves. In modern physics, however, we no longer need such a medium to explain the propagation of light. But in the context of digital physics, we might revisit the concept of ether, not as a physical substance, but as a medium made of information. Instead of thinking of space as a void or a vacuum, we can imagine it as a dense network of data, constantly updating and processing itself. This digital ether would represent the most basic layer of reality, the underlying grid upon which all other physical phenomena unfold. Every particle, every interaction, every law of physics could be seen as a manifestation of this vast computational process, encoded in the fundamental bits of information that make up the universe. The idea is that space-time, the very stage on which the drama of the cosmos unfolds, is a discrete structure built from tiny informational units. In a sense, the material universe could be viewed as a projection of information. Just as a computer screen displays images made up of millions of tiny pixels, our physical universe might be a kind of screen displaying the results of a computational process. The difference, of course, is that the pixels of the universe are not two-dimensional and static, but are dynamic and three-dimensional, governed by the laws of physics. For example, the way particles interact with each other in quantum mechanics could be understood as the result of the manipulation of information at the quantum level. Rather than particles existing as fixed objects with definite positions and velocities, they might be better understood as packets of information that exist in multiple states until measured or observed. This is similar to the way a computer program can represent multiple possibilities at once, processing them until a final outcome is determined. The act of collapsing a wave function might be akin to selecting a particular outcome from a range of possibilities within the computational system of the universe. Information in this context is not just abstract data, but an active force that governs the behavior of the universe. It is the very code that determines how the universe operates, how particles interact, how energy flows, and how structures form. If we think of the universe as a computer, then everything from the tiniest particle to the largest galaxy can be seen as a result of the processing of information at different scales. One aspect of this view is that it suggests the universe might be fundamentally algorithmic. These algorithms could be seen as the program that runs the entire universe. Just as a computer program executes a series of instructions to create images, sounds, or behaviors, the universe executes the laws of physics to create the reality we experience. In this way, the fundamental forces of nature could be understood as expressions of deeper computational rules that process information at a fundamental level. The interaction of these forces could be seen as the result of the exchange and transformation of information. Spacetime is seen as a continuous and fundamental element of reality. However, if space and time are emergent from a deeper computational process, they might not be fundamental at all. Instead, they could be seen as the result of how information is processed in the digital ether, emerging from the underlying code that governs the universe. Time itself, in this view, could be a byproduct of the flow of information, with the arrow of time corresponding to the direction in which data is processed. This shift in perspective also brings with it fascinating possibilities for understanding the nature of reality itself. If information is the fundamental substance of the universe, it raises the question of what happens when this information is altered or corrupted. In the same way that a glitch in a computer program can produce unexpected behavior or even breakdowns in the system, disturbances in the flow of information in the universe could have profound effects. These glitches might even help explain some of the unexplained phenomena we observe in the cosmos. If the universe is driven by information, does that mean that information itself is alive in some sense? Could the processing of information be a form of thought on a cosmic scale? Just as our brains process information to produce thoughts, perceptions, and actions, could the universe itself be processing information in ways that we have yet to understand? Could consciousness, in some way, be a byproduct of the information flow in the universe? What do you think about this kind of possibility? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.